Yes, you can start. So now our next speaker is Pranab from the Tata Institute of Fundamental Research, and he will be talking about fully smooth covering of quantum states, telescoping, flattening, expander matrix Chernoff. The floor is yours.
Okay. Yeah, thank you very much for giving me an opportunity to speak at Beyond IID. And I'm unfortunately not able to be there in person, so sorry about that. I'm grateful for this opportunity to give an online talk. So the title is quite a mouthful: fully smooth covering of quantum states, telescoping, flattening, expander Chernoff. It's based on 3 papers which are out on the archive. Okay, so let's go through these topics slowly, and I'll give a very high-level overview of the works. Okay, let's start with something that is easy. What is soft covering of quantum states? And to make the notation very precise, I will call it unipartite soft covering of quantum states. So in this problem, what is given is an ensemble of quantum states, okay, so which are indexed by a classical symbol X. So the little x comes from a classical alphabet capital X, and all these states live in the same Hilbert space M. Okay, there's a certain probability distribution Px on the symbols X, and epsilon is some real number between 0 and 1. The task is we choose n samples. For the set of samples I'm calling S, and I'll call my samples row x1, row x2, dot, dot, row xn. These samples are chosen in an IID fashion according to the distribution Px. Okay. So here is the question. So to define the question, let me first define some quantum states. So there is this classical quantum state rho xm, which is as follows. X is chosen classically according to distribution Px, and condition on X, yeah, there should be tensor product here, sorry. So condition on X, the state on M is rho sub X. And this row subscript set S is just the sample average. So I've chosen the samples, right? So I'm just taking the sample average of these quantum states. So the question here is, how large should the number of samples N be so that the sample average row subscript S is close to the marginal rho M, the true marginal rho M in L1 distance. So let's say I put some bound 3 epsilon. I want it to be close. Now, of course, the distance of the sample average state from the true marginal depends upon the choice of samples. Okay, so this is actually a random variable. I want the expectation of this random variable to be less than 3 epsilon. So the question is, how large should n be so that the expectation of this distance from the sample average to the true marginal is less than epsilon? So there is some answer for this. So the smooth unipartite convex split lemma of Anshu, Devavatini, and Jain says that if log n is larger than this quantity, so if the number of samples is sufficiently large, so how large is sufficient large? So log n should be larger than the smooth max mutual information between X and M under the state row. So this is the state row which we have. And then there is an additive term to log 1 by epsilon. So as long as the number of samples is larger than this quantity, this expectation will be less than 3 epsilon. Okay. Now, here is a new question. So this is soft covering, unipartite soft covering, but in expectation. Now, the new question is, suppose we have this lower bound on log n. So we have covering in expectation. The question is, do we have covering in concentration? So what do I mean by that? Suppose the distance between the sample average state to the true marginal deviates away from the expectation. So it should be larger than, let's say, 3 epsilon plus delta. So the expectation I know is less than 3 epsilon, but the question is, suppose I'm deviating additional delta away from the expectation. So this probability should be small. So the question is, does it have a tail bound which decays exponentially in the number of samples? Okay, n delta square and then something else. We'll see what it is. Okay. So this is what I mean by soft covering in concentration. So in this talk, we'll see that yes, we do get unipartite soft covering in concentration. And we can think of this as a new matrix Chernoff bound. Okay. So this tail probability is smaller than the famous Alstead-Winter matrix Chernoff bound. Okay, if you compare the two. More importantly, there is no Hilbert space dimension dependence in this tail bound. Okay, so I'll tell you precisely what the tail bound is in the next slide. But indeed, it looks like n times delta square, and this dot 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 does not hide any dimension. By dimension independence, I mean it's independent of the dimension of m. Okay. But the caveat is that Elser-Winter actually guarantees a stronger result. They actually guarantee an operator inequality in concentration, whereas we are only guaranteeing closeness in the L1 norm. But then again, as the next application shows, in many information theoretic problems, closeness in L1 norm suffices. Okay. So here's an application. So this gives the first inner bound for sending private classical information over a point-to-point quantum wiretap channel with T non-interacting eavesdroppers. So the usual wiretap channel, if you know, I mean, there's a sender, there's a receiver, and then there's an eavesdropper. So there's one eavesdropper. Now the question is, suppose there are T non-interacting eavesdroppers. Okay, so non-interacting is important. If they interact, then it's like one big eavesdropper. But here we have T non-interacting eavesdroppers, and the aim is to do secure communication from Alice to Bob, and none of these eavesdroppers individually should know anything about the classical message being sent. So of course, the achievable results are expected to degrade with T. The more eavesdroppers you have, the more difficult it becomes to maintain privacy against all of them. So the goal here is to get an inner bound which depends only logarithmically on the number of eavesdroppers and is independent of the dimensions of the Hilbert spaces of the eavesdroppers. Okay. And it turns out to achieve all this, what we do need is a matrix Chernoff bound where the tail bound looks like this. There is no explicit Hilbert space dimension dependence. Okay. And yeah, so basically the log T comes because this exponential in minus n has to be less than T. So somewhere, I mean, that converts to log T, very roughly. Okay. So how do you prove this soft covering in concentration? So we actually appeal to McDermott's concentration inequality, which is also known as the method of bounded differences. So let's define a function from x to the power n. Recall x is the classical alphabet. So like n copies of the alphabet to real numbers. And this is the definition of the function. So for a tuple of alphabet symbols, x1 to xn, this is what is the value taken by the function. Okay. And this function satisfies a bounded difference property. So let's look at the ith coordinate of this function. Okay. So to define the ith bounded difference, what we have to do is we maximize over all possible symbols x1 to xi minus 1. Okay. Then, sorry, this should be xi plus 1 to xn. So fix arbitrarily symbols x1 to xi minus 1, xi plus 1 to xn. But in the ith location, we can have variation. So in one case, we have symbol xi. In another case, we have symbol x prime I. Okay. Now, if I maximize over all possible settings of these symbols where there's variation only in the ith coordinate, the question is how much can the function vary in absolute value? So it's not hard to see by triangle inequality on the L1 distance that this variation is upper bounded by this quantity. Okay, so I can forget about all the other symbols x1, xi minus 1, xi plus 1, xn. I can only look at the ith symbol. So it's either xi or it's either xi prime. How far can they be? They can be at most a distance 2 n L1. So di is upper bounded by 2 by n. So then McDermott's inequality says that if such a function from a Cartesian product space to real numbers satisfies bounded differences, then it cannot deviate from its expectation by much. Okay. So so the tail bound is if you have to go delta away from its expectation, so it drops off like this. Okay. And now if we put in our value for di, which we calculated here, we get this tail bound. Okay. So that's it. So this is the new matrix Chernoff bound. Okay. And as you can see, there is no Hilbert space dimension dependence out here. Okay, so finally we have proved this matrix Chernoff bound larger than 3 epsilon plus delta. Remember 3 epsilon was the expectation of this function. Okay, so it drops off like this. Okay, so this leads us to a new question. Okay, so consider the case that the probability distribution on the alphabet is uniform. Okay, now let us say on the alphabet we put an expander graph. Okay, so the vertex set of the expander graph is my alphabet X. Okay, so my expander graph is the usual thing. It's an undirected constant degree regular graph. And instead of choosing the n samples x1 to xn IID uniformly, which we were choosing earlier, okay, for our expectation as well as our concentration result, matrix Chernoff result. So what we do is we choose x1 uniformly and then choose the remaining samples x2, x3, x4, etc. by performing expander walk on G, right? So choose x1 uniformly, then do one step of an expander walk that gives x2, second step of the expander walk that gives x3, so on. Okay, do n steps of this expander work. The question is, can we still get unipartite soft covering in concentration out here? Okay. So in this talk, we'll answer this question. So the answer is yes. It's actually a new expander matrix Chernoff bound. So earlier, Garg, Lee, Song, and Srivastava proved an expander matrix Chernoff bound. So they were following the lines of the Alsted-Winter matrix Chernoff bound, but they did it for expanders. But they measure the distance from the sample average state to the marginal using the Shannon L infinity norm. Okay, this is because, I mean, somewhere the operator inequality of Alsted-Winter converts to the Shannon L infinity norm out here. Unfortunately, the bound that Garg et al. Proved becomes useless if you want to infer closeness for the L1 bound. I mean, if this conversion from L infinity to L1 loses a lot for Garg et al.'s bound. So, whereas our expander matrix Chernoff bound is actually tailored for L1. Okay, so we prove our expander matrix Chernoff bound by actually going back to McDiarmid, but this McDiarmid inequality required independence in the choice of samples x1 to xn, full independence. Okay, so we cannot actually use McDiarmid's inequality off the shelf. So you have to generalize McDiarmid's method to a new tool. So it's a new concentration tool. So we call it the method of bounded excision for expander graphs. Now, McDiarmid's inequality is usually proved in textbooks by martingales, but they're unsuitable for the bounded excision setting, okay, as we'll see. So instead, we prove bounded excision by actually going back to a different proof of McDiarmid's inequality. So this proof was given by Ying in 2004, and it's actually absolutely an elementary proof of bounded differences. So we actually go to that proof and extend ideas from there, and they turn out to be simple enough that we can extend to expander graphs. So, but first we'll define what is the method of bounded excision. So again, we have a function from the n-fold Cartesian product of the alphabet to R. So it satisfies bounded excision with parameters. So now the parameters are a little complicated to find. So there's one bounding parameter C, and for every pair of indices L1, L2 between 1 and n, there is a parameter C subscript L1, L2. Okay, so what we want is, so here is the excision part. So take the function, okay, evaluate it on a certain tuple of symbols x1 to xn, but look at the block of symbols from L1 to L2. So that's the central block out here. Now suppose I remove that block, I excise that block out completely and evaluate the function on a smaller tuple. So the variation should not be much. It should be bounded by this parameter CL1, L2. Okay. And secondly, when I'm looking at the excised function, so now I'm evaluating a smaller tuple, this is an overall bound, okay, of C. So this is what the set of parameters C and CL1, L2 mean. So once we have bounded excision, we can actually prove a concentration inequality for such a function. So let lambda be the second largest absolute value of an eigenvalue of G. So here's the concentration inequality. So the probability over the choice of samples, but now they're coming from an expanded walk. So the probability that the function deviates from its expectation by more than delta has an exponential tail bound, which looks superficially like McDiarmid, but now we have to define these DIs. So these DIs are a little complicated. So these DIs depend upon the parameter like C I to I plus A, and then there is something else out here. So what is A and B? These are things that depend on the size of the alphabet, then the eigenvalue, and B in fact depends upon the parameters also. But what is the take-home message? So forget about all that. So the idea behind bounded excision is that let us excise out blocks of length A and B. Okay, so I'll excise out two blocks. I'll excise out a block of length A, and then I'll excise out a block of length B of the tuple. So the block of length A, I'll excise out starting at position I. So from I to I plus A, I have excised out that block. And then from I plus A plus 1, I excise out a further block of length B. The thing is, because of bounded excision, if we excise out these blocks, the function value does not change too much. And the lengths of these blocks, which are given here, A and B, are large enough to make the samples before and after the excise block. So so coming back here, so the sample at I minus 1 and the sample at after all the excision. So like I plus A plus B plus 1. Okay, so the samples before and after the excise blocks are sufficiently far apart that the expander walk makes them almost independent from each other. Okay, so these are the ideas behind the proof. So with these ideas, we can make Ying's elementary proof of McDermott go through, and we finally get this bound. Okay. So from the method of bounded excision, this is the new matrix, the expander matrix Chernoff bound that we can prove. So I'll again not bore you with this. So as you can see, there's no dependence on the Hilbert space dimension M, but unfortunately there is a dependence on the alphabet size log x out here. There's of course a dependence on the eigenvalue of the expander lambda. And otherwise it's dropping like n times delta square. N is the number of samples. And this first part as usual is capturing the expectation of this function, 2 square root epsilon. So so the expectation is at most 2 times square root epsilon if the number of samples n is large enough. How large enough? So it's sort of what you expect before. It is I max epsilon of x colon m. So this is what the smooth unipartite convex split would give you. But then there are other technical reasons. We have to add in something more. Again, this there's a log x term, so which is the alphabet size coming. Okay. And to prove this matrix Chernoff bound, so we have the same function as before. Okay, so it turns out it satisfies bounded excision with these values of the parameters. So the overall variation is at most 2, and the L1 to L2, like if I excise from position L1 to position L2, excision of this block changes the value of the function by at most this much. Okay. So let's go ahead. So this was unipartite soft covering. So let me define what is multipartite soft covering. So now I have an ensemble of quantum states, but so I look at bipartite soft covering. So now there are two symbols x, y. So they come from two alphabets, capital X, capital Y. And let's say I have independent probability distributions px, py on them. The task is choose m samples x1 to xm IID from px, n samples y1 to yn IID from py. And the question is, okay, so let's define. So though I've only chosen m samples here and n samples, so totally I've chosen m plus n samples of symbols, the states that I'll consider are m times n. So for every xi, yj, I look at the corresponding quantum state. So this is a set of size mn. Okay, but I define the CQ state rho xyz similarly as before. So this is the sample average rho sub s. Okay, so I'm taking the average over this set, and remember this set is of size mn. Okay, and the question here is how large should m and n be so that the sample average is close to the marginal in expectation. So again, there's an answer which was known. So then answer comes from the non-smooth multipartite convex split lemma of Anshu, Jay, and Varsi. It says that the following conditions satisfy. So if the number of samples is sufficiently large, so that means log m is larger than this max mutual information. Note that this is a non-smooth term out here. So again, there's a non-smooth term. Log n is larger than this max mutual information. And log n plus log n has to be larger than the corresponding max mutual information. Okay, so if all these three conditions satisfied, then the expectation is less than 16 epsilon. So now the question here is, just as in the unipartite case, can we get bounds in terms of the smoothed quantities I epsilon max? We don't like the non-smooth quantities. So we want bounds for the smoothed quantities. But unfortunately, trying to prove it is not easy. So this hits the so-called bottleneck of simultaneous smoothing. So actually, the smoothed bound in the unipartite setting was proved by replacing the actual states, rho x, by some suitably perturbed versions, which I'll call rho prime x. So rho prime x is close to rho x in L1, let's say. Now, this rho prime x individually satisfies the operator inequality with respect to the marginal with the smooth I max out here. So for every x, rho prime x is the smoothed version which satisfies this operator inequality. So we have to first replace the samples by their smoothed versions, and then we run a different non-smooth proof on the rho prime x. So this was how it was done for the unipartite case. Now, if you try to mimic this strategy for the multipartite case, we run into the following problem. So one has to find suitably perturbed versions rho prime xy, okay, of the original states rho xy. So of course, the perturbed version should be close. So, but what do we require? For all xy, we have to satisfy three different operator inequalities, okay, for suitable margins. So rho prime x is obtained by taking rho prime xy and averaging out y according to py. So similarly, rho prime y is defined similarly. Yeah. So simultaneously, all the three operator inequalities should be satisfied. So what we want is a single perturbation rho prime xy of rho xy that satisfies simultaneously three operator inequalities, and they have a priori three incompatible smoothings. So normally, if I have to smooth, let's say for I max epsilon y, that smoothing will be incompatible by what I have to smooth for I max epsilon x. So basically, the smoothed operator smoothed states will not commute with each other. So the question is there some golden single perturbation which satisfies all this? Maybe it's some fudge factors. Okay, so this is an open problem. It's a major open problem in quantum information theory. Nevertheless, a couple of years ago, so there was a very important progress towards a smooth version of multipartite convex split by Cheng, Gao, and Barta. And similar progress was made towards a smooth version of multipartite decoupling of quantum states by Colomer and Winter. So both these works actually bypass simultaneous smoothing. They discovered a new proof technique called, which I would like to call telescoping cum mean zero decomposition. However, these works still did not prove the fully smooth lemmas that we desire. I mean, maybe they were smooth in one register, but not smooth in the other register, things like that. So by fully smooth, I mean it should be smooth in all the registers, X, Y, Z, etc. So in this work, we prove fully smooth multipartite convex split and decoupling lemmas for the first time. So we do it by various techniques. So the first technique is actually revisiting telescoping. So we clean up the description of telescoping, which allows us to do a better analysis of the telescoping cum mean zero decomposition technique. Okay. So we end up showing that yes, the sample average state is close to the margin in expectation, provided the number of samples is large enough. But now we have the smooth max mutual information out here. And this is smooth in all the registers. All three are smooth quantities. Okay. And our proof technique shows us something even more. It says that even if the X samples and Y samples are chosen pairwise independently, they don't have to be chosen IID, they just have to be chosen pairwise independent from the respective distributions. Still the result holds. Okay. The only thing is that the X sample should be independent from the Y samples. But within X, they are pairwise independent. Within Y, they are only pairwise independent. The same result holds. Okay. And how do we prove this? So the proof starts by some following definition. So remember, this is the quantity whose expectation we want to bound. So I'm giving it a name Fs. Okay. So I'll just rewrite it this way. I mean, I'll pull in rho z into the brackets. Okay. And this quantity, I'm going to replace it by sum of three terms. okay, which are defined here. I'm giving them different names. So sigma z xy is defined like this. And this is called the telescopic part of the proof. So if you see, like if you add sigma xy to sigma x to sigma y out here, you will actually get back rho xy minus rho. Okay, so this is like a telescoping sum. So this is the telescoping part of the proof. We have to first replace it like this. So far nothing really new has been done. But now here's the clever part. So we can replace sigma xy by a perturbed matrix, which I'll call sigma 3xy, which is defined like this. What is rho 3xy? Rho 3xy is close to the original state, but it is a smoother state that achieves only this operator inequality. Remember, one had to achieve three different operator inequalities by the same smoothing, but now we are less ambitious. We are only talking of the smoothed version which achieves just this particular operator inequality. We are not going to be bothered about the others for now. So this is rho 3, and from rho 3xy, we can similarly define rho 3x by averaging out y and vice versa. Okay, so this is the definition of sigma 3. And one can immediately prove that sigma 3 also satisfies the same operator inequality with maybe a factor of 4 out here. Sigma 3 is also close to the original sigma xy out here. So far, so good. Okay. Now, similarly, we can replace sigma x by a perturbed matrix which I'll call sigma 1x. So define like this with rho 1x. So rho 1x is actually the smoothed state that achieves this operator inequality. I don't care about achieving the other operator inequalities out here. So again, sigma 1x satisfies this operator inequality is close to sigma x. So similarly, sigma y is replaced by sigma 2y. So it turns out that upper bounding this distance by triangle inequality reduces to upper bounding the sum of these three quantities. Okay. But then what we can do is that we can replace the first one by sigma 3. This I can replace by sigma 1, then by sigma 2. So we can replace each of these three terms by separate smoothings. So this is the beauty of telescopy. And then each of these three terms we can bound separately by the matrix Cauchy-Schwarz inequality. So I'll not again delve into the steps. But the key steps in applying it is that one has to upper bound quantities which look like this. Okay. So right now I'm only focusing on the first term. So I've replaced sigma xy by sigma 3 xy, the perturbed versions. But you can see the expectations are slightly different out here. Now, traditionally, this is where simultaneous smoothing was still a bottleneck because there are different expectations. But here is where the beautiful thing happens. So observe that in sigma 3 xy, if I just average out x, or if I just average out y, and if I average out both, I'll get 0. So this is what I would like to call the mean zero decomposition technique. So remember, I said we have to analyze these 4, but 3 of them average out to 0. The only non-zero term is the first one out here, just expectation over x. So we only have to analyze this term, and this we can analyze by the operator inequality. Only one operator inequality is necessary out here, so we get this. So see, we have got one smooth Imax term out here, and the other two terms for sigma 1 and sigma 2 can be analyzed similarly. So finally, if we package all these things together, we get the smooth bounds as desired. Okay, so the proof immediately makes clear that only pairwise independence amongst X samples and Y samples are required. And ultimately, it is because of matrix Cauchy-Schwarz, which is a degree 2 bound. Now, in order to get multipartite soft covering with concentration, we can apply McDermott's inequality as before. So this gives us the first multipartite matrix Chernoff bound. So here's an open problem. Can one get a multipartite expanded matrix Chernoff bound? Unfortunately, we could not prove this, so the problem still remains open. So if you try to mimic the proof of the unipartite expander matrix Chernoff using Ing's methods, we again hit the simultaneous smoothing bottleneck, and this time it hits us very badly. Okay. Informally speaking, it hits us very badly, I mean worse than before. So we have no way of going around it. But what else can we do? So we note that choosing samples via expander walks destroys pairwise independence. Even for practical considerations, it's sometimes interesting to ask if one can prove a smooth multipartite soft covering result when there's a mild loss of pairwise independence. So in this work, we actually managed to prove a fully smooth, again smooth in all registers, multipartite soft covering result under a very specific definition of loss of pairwise independence. Unfortunately, this definition does not cover the case of random walks, but nevertheless, it's a start. So, so right now we don't have a concentration result. We are only proven expectation result. So to prove this expectation result under loss of pairwise independence, it turns out we have to drop telescoping. Again, telescoping fails badly if pairwise independence goes away. So we use a different observation. So we actually revisit a certain flattening procedure from classical probability theory, but we apply it to quantum states. So applying it to the quantum state rho z gives us a new state, which I'll call rho z z prime. So this lives on z together with a new register z prime. The beauty is that this new state in the extended Hilbert space z z prime is actually completely mixed over a subspace of z z prime. So that's where the name flat comes, flattening. So this is not very new, but our new contribution here is that this flattening CPTP map actually preserves the fidelity between the sample average state and the marginal. So this is a new observation. So the power of this observation is that since the flattened state rho z z prime, okay, it's completely mixed, right? It's flat. We get nice commutation properties if we try to apply the matrix Cauchy-Schwarz inequality directly to this. So early in telescoping, we broke this up into a sum of 3 terms, the telescoping part. Here, we are not going to break it. We are going to hold our breath and directly apply matrix Cauchy-Schwarz to this. Okay, in so doing, it really helps that this rho z z prime is now flat. So the nice commutation properties. So the problem reduces to upper bounding this trace of rho z z prime subscript s square. Okay, so upper bounding this L2 quantity. So this quantity turns out can be upper bounded after some effort in terms of smooth entropic quantities, but we have to use further techniques from earlier work, which are called tilting and augmentation smoothing of quantum states. Okay, so it's again not direct. We need a fair amount of work, but it turns out this can be upper bounded. And doing so gives us the first unipartite as well as multipartite soft covering result in expectation. And this is the first result even in classical as well as quantum information theory that holds under loss of pairwise independence. So I'll stop for now. Thank you for your attention.
Thank you for the nice talk. Any question from the audience?
Thanks for the nice talk. So, Pranab, is there a specific reason why you consider X1 like being sampled according to a random walk on the expanders in the first place?
Okay, so the so the expander walk is important for certain de-randomization applications. So so part of the reason is just purely mathematical, but indeed an expander matrix Chernoff bound. So this paper, this Garg et al., which I referred to here, this work, Garg, Lee, Song, Srivastava. So they do have concrete motivation. So so their expander matrix Chernoff bound, which they prove, they apply it to certain de-randomization results in classical computation complexity theory. Okay, so this is actually not a quantum paper at all. So this is applications even for de-randomization problems in classical computation complexity. Now, the point is the first vertex, even if you choose it from some other distribution, the expander walk will eventually make it uniform. Okay, so that's the property of the expander walk, right? Rapidly mixing.
Yeah.
So, so to make matters simple, we just assume that X1 is chosen already uniformly, which is the station distribution, and then start the expander walk from X1, get X2, X3. But now we have lost pairwise independence. So the question is there still concentration in any sense? And the answer now is yes.
Okay, thanks.
Yeah, thanks for a nice talk. I have 2 questions. The first question is, have you considered similar thing for multipartite convex splitting?
Yes, yes, I have considered. I think I did mention it. Oh, yeah, you mean a multipart expander matrix Chernoff?
In a convex splitting sense, that you have this.
Yeah.
Sorry.
Yeah. So, okay. So, multipartite convex split expectation is this basically. What do we get?
You have the
This,
Dmax.
yeah, d max epsilon. So this is a multipartite convex split. Okay, but in expectation, it just says that the expectation over the samples of the L1 distance between sample average state to the true marginal is small. Okay. So that's already done, and that we can prove by telescoping. We can also prove it by flattening, but anyway, telescoping is a much shorter proof. The question which is open is, can we prove a concentration version of this? So we choose the samples x1 to xm, y1 to yn, IID. Sorry, not I. If the chosen IID, we also have concentration results. So that's multipartite matrix Chernoff, not expander matrix, multipartite matrix, independent matrix Chernoff, let's call it. So that also I think I mentioned here. Yeah, multipartite matrix Chernoff. So this we can do by again applying McDiarmid inequality. So what do we have? We have multipartite convex split in expectation, fully smooth. We can get multipartite convex split in concentration by applying McDiarmid. The only thing that is open is multipartite convex split in concentration where the samples come from an expander walk. Okay, that's the only thing which is open. And this we are unable to prove. So this is where, I mean, if you try to repeat the proof, so the details are there in the paper, I mean, you'll get the feel why simultaneous smoothing hits us, and it hits us very badly. Okay, so the point of this work is that, because of the setback, can we ask, okay, fine, I mean, we have lost pairwise independence. Can we at least get a result for expectation with loss of pairwise independence? And the answer to that is yes. Okay, under a very specific notion of loss of pairwise independence, we do get multipartite convex split in expectation, but this definition still does not meet the definition of random walks, but it's just a start.
Okay. Another question is that for convex splitting, if you choose the first party to be classical, then you reduce to the soft covering.
Correct.
So you can reduce the multipartite convex splitting to a multipartite soft covering results.
Correct.
How that will compare to your IMAX expression? IMAX.
Oh yeah, so it's the same thing. So actually, the paper. I mean, in these works, there are separate sections. So there is a fully quantum statement of multipartite convex split, X, Y, Z, but where X, Y, Z are all quantum. Okay. And it's exactly what you expect. And then I specialize to the case where X and Y are classical. So multipartite convex split becomes multipartite soft covering. So the definitions are exactly the same. I mean, so.
Okay.
Yeah, so I think, right, I mean, somewhere I defined this. Yeah, right. So, so there I straight away start off with rho XYZ. I mean, there is no such description, and XYZ are all quantum. And the analogous statements hold. The same telescoping cum mean zero technique holds there, actually. Okay. And even the flattening technique also holds there. So all this run parallel. The difference is, why am I interested in soft covering is, well, I mean, many people have considered it. It's an important special case. Also, if I have to talk of loss of pairwise independence, I do not know what would be a fully quantum formulation of loss of pairwise independence.
Sure.
Okay. So that's a very curious problem, I think. Yeah. So though, I mean, flattening works for fully quantum multipartite convex split also. I mean, the real power of flattening comes in once I come down to soft covering, and then I can talk of loss of pairwise independence amongst the classical samples. There's only one quantum register now, and that's where flattening really does something which no other technique can do.
Okay, thanks.